Hello and welcome to Sleepy Science Story. This is your time to slow down, to let the world soften at the edges, and to drift somewhere quieter for a while. Tonight, we're going to float through the mysterious final chapters of the universe's most dramatic storytellers, the supernovas. These are not quiet endings but brilliant finales flaring into the darkness like celestial sighs. And don't worry, we'll take it slowly, like starlight traveling through time. I do hope this story isn't so interesting it keeps you wide awake, but if it is, at least you'll fall asleep knowing why the atoms in your bones once belonged to a star that lived loudly and died beautifully. Some stars live quietly, flickering steadily through the centuries, content to glow and fade with time. But others are louder, more theatrical, with hearts too full of energy to last. These stars are the ones that burn faster, shine harder, and refuse to go gently when their time comes. Their ends are not soft curtain calls but grand finales that light up the cosmos like a million fireworks bursting at once. Imagine a star that has spent millions of years building layers within itself, fusing element after element deep in its fiery heart, each one a step closer to its undoing. At first, it hums along just fine, comfortably fusing hydrogen into helium, like many of its quieter neighbors. But as it ages, it grows hungrier. It starts fusing heavier elements, stacking them like an anxious baker making a cake far too tall. Eventually, this star reaches a point where it begins to produce iron in its core. And this is where things start to unravel. Iron is heavy, and it doesn't give back the energy the star needs to hold itself up. So the delicate balance that kept everything in check begins to tip. Gravity, which had been politely kept at bay, begins to lean in, and not just lean in gently, it pounces. The core collapses in on itself, a sudden implosion faster than anything we can to really picture. It happens in less than a second. It's the kind of speed that makes light feel sluggish, and in that collapse, something extraordinary happens. The outer layers of the star rebound off the dense, crushed center and explode outward. The star doesn't just die, it erupts. This is the supernova, a stellar swan song that, for a brief time, can outshine an entire galaxy. It is brightness on a scale that overwhelms human thought. If it were to happen close enough to us, it would be visible during the day, it would cast shadows at night. But most of the time, these brilliant goodbyes happen far away, in distant arms of the Milky Way or beyond, playing out like cosmic theatre performances we can only observe through telescopes. For the star, this is the end of the line, but for the universe, it's the beginning of so many other things, because in that explosion the star flings its insides into space. All the elements it worked so hard to create get scattered into the galactic winds. This stardust drifts, joins clouds, meets other dust, and eventually forms new stars, planets, and even living things. So while the star's life ends in a violent flare, its story doesn't stop there. It becomes part of countless others, which is rather comforting, isn't it? A loud goodbye, echoing quietly forever. A star that lived too loudly to fade away without being noticed, and ended up leaving a trace in everything from golden rings to the calcium in our bones. It's a strange name, really. Supernova. It sounds almost too cheerful, like something you'd find painted on the side of a rocket-themed amusement ride or scribbled in a child's notebook. But the truth of a supernova is something far older, quieter, and deeper than the name lets on. It is not a single thing, but a moment, a kind of stellar punctuation. It is what happens when a star reaches the very end of what it can do to keep itself from collapsing. Imagine a life lived in balance, one where the outward push of heat and fusion meets the inward pull of gravity, and then one day, gravity wins. Not in a loud, angry way, more like a final exhale after a long life. That's what a supernova is. It's the soundless shatter of a balance that held steady for millions of years. And yet, the result is one of the brightest things the universe can offer. In those fleeting weeks when a star goes supernova, it shines with more light than all the other stars in its galaxy combined. If you could see it up close, which thankfully you cannot, it would be blinding. Pure white-blue light, rippling outward, changing the very shape of space around it. But it is more than just light. It's also heat and matter and energy rearranging itself in spectacular fashion. A stellar finale so powerful that it sends shockwaves rippling through clouds of gas and dust light years away. Scientists have tried to pin down the moment, to define exactly what a supernova is, and like most cosmic events, the definition remains soft at the edges. But broadly speaking, a supernova is the explosion of a star at the end of its life. It's not an explosion in the way a balloon pops or a firecracker bursts. It's more like a dam breaking, pressure long held finally releasing in every direction. And unlike the explosions we're used to here on Earth, a supernova happens in silence. There is no medium for sound to travel through in space, so even the most violent stellar destruction unfolds in complete quiet. No roar, no bang, no echo. Just light blooming where there was once only a steady star. And then, just as quickly as it began, the light begins to fade. Within weeks, what was once the brightest object in its corner of the universe becomes invisible again to the naked eye. Only traces remain. The spreading shell of gas, the fragments of heavier elements, and sometimes the dense core of what used to be a star. These leftovers go on to live new lives. They might become part of a nebula. They might collapse into a neutron star. They might vanish entirely into a black hole. But always, something remains. So when we ask, what is a supernova? Really, perhaps the gentlest answer is this. It is the last great thing a star can do. Its final burst of beauty, a gift to the universe, wrapped in light. Before a supernova announces itself in brilliance and color, there is a strange kind of stillness, a quiet pause in the life of a star, as if the universe itself is holding its breath. This stillness can last for millions of years, but in the scale of a star's life, that is the final heartbeat before the silence breaks. It is a phase filled with invisible tension. Inside the core of a massive star, fusion continues its tireless work, transforming elements one after another. The outer layers burn with familiar light, unchanged to any observer peering in from afar. But inside, things are slowly slipping. The core is filling with iron, and the star is running out of options. It cannot fuse iron to create energy. That path is closed. And so, the star begins to edge toward collapse. Imagine a colossal engine running out of fuel. All the pressure that once pushed outward now has nothing to hold it back. Gravity, always patient, begins to lean in, but it does not do so suddenly. It presses gently at first, like water seeping into cracks. That is the quiet before the blast. The slow, inevitable shift from balance to breakdown. From the outside, the star looks as serene as ever, still shining, still drifting in its celestial lane. But within, the center is growing heavier. The iron core grows denser, tighter, more fragile, and at some point, though it is impossible to mark the exact moment, the pressure becomes too much. The core can no longer bear its own weight. What follows is not a graceful surrender. It is a collapse so fast it might as well be instant. The inner parts of the star fall inward at a fifth of the speed of light, faster than thought, faster than past. Fire! This inward rush causes the core to stiffen suddenly, as if the very atoms cry out against the pressure. And in that stiffening, a shock wave is born. But we are not there yet. We are still in the quiet. The the moment just before that final drop. This phase, the calm before the cataclysm, is a mystery we can only imagine. We cannot watch it in real time. No telescope can peer through the outer layers of a star to see the precise second gravity takes over. All we know is that it happens in silence. Stars do not scream when they collapse, they simply stop resisting. And then, just like that, the quiet breaks. But in this segment we rest in the pause, the long exhale, the heavy stillness of a dying star pretending, just for a little longer, that nothing has changed. Perhaps that is why the idea of a supernova holds such weight, not only for its bright end, but for the hush that comes before it, a hush filled with tension, with waiting, with the soft ticking of a cosmic clock whose hands are about to fall. And once they do, nothing will ever be the same. At the heart of every massive star is a furnace, a place where elements are built layer by layer like a slowly rising cathedral. It begins simply, with hydrogen fusing into helium, then helium into carbon, then carbon into heavier things. Each new layer takes more energy and burns hotter than the one before, but no matter how powerful the process becomes, it is always under pressure. The star fights a constant battle to hold itself up, to keep gravity from pulling everything inward. As long as fusion continues, the star wins. But eventually, it reaches a point where the fuel no longer gives back. That moment comes with iron. Iron does not play by the same rules as lighter elements. Instead of releasing energy when fused, it steals it. So when a star builds an iron core, it is unknowingly preparing for its final act. The fusion engine sputters. The outward pressure that once balanced the inward pull begins to fade. Gravity, patient and silent, starts to tighten its grip. The core shrinks, compresses, and in a matter of moments, it becomes something impossibly dense. The atoms that once had space between them are crushed together. Electrons are slammed into protons, and new particles called neutrons take their place. In that flash of collapse, a neutron core forms. But not gently. It slams into existence with a force that sends ripples through space. Imagine the entire mass of the sun being squeezed into a ball no wider than a city. That is the heart of the dying star now. A sphere of neutrons, hot beyond comprehension and harder than anything found in nature. Around it, the outer layers of the star are still falling inward. They hit this new surface and rebound outward like a tidal wave crashing into a cliff. That rebound is the beginning of the explosion. A wave of energy and matter races outward, throwing the star's outer shell into space. Light, radiation, elements, and heat all spiral out in every direction. And yet, at the center, there is silence. The collapsed core does not speak. It does not shine. It simply exists, dense and strange, a remnant of the star's final heartbeat. This sudden transformation from balance to collapse, from fusion to implosion, is the tipping point of the supernova. The moment the star stops being a furnace and becomes a memory. It is a change so swift and so total that it leaves the universe reshaped in its wake. For a moment, there is chaos, but not long after, there is peace again. The light travels, the energy disperses. What remains is a shell of gas and a quiet, spinning core. This core may one day become a neutron star, or, if the collapse went far enough, it might vanish entirely into a black hole. But either way, the star's final heartbeat has passed. What follows is only the echo, a beautiful expanding silence filled with stardust and memory. Imagine soundless thunder rippling through space, not in the way a drum shakes the air, but in a way that shakes the fabric of everything. That is what happens when a supernova finally lets go. After the collapse of the core, after gravity has won, and the heart of the star has become a dense neutron-packed sphere, something remarkable happens. The rest of the star, all those layers of gas and fused elements, begin to fall inward. They crash against the newly formed core with incredible force. The rebound is immediate. It is not slow. It is not soft. It is sudden, powerful, and immense. This rebound is where the explosion begins. A shockwave forms at the core and races outward, carrying the matter of the star with it. At this moment, the star is no longer a single object, but a symphony of motion and pressure. The materials it once held so carefully are now being hurled into the darkness at speeds that defy easy comparison. Some parts travel faster than 10,000 kilometers per second. That is fast enough to circle the Earth in less than a second, if only the Earth were in the way. But instead, space stretches out in every direction, ready to receive the pieces of this stellar release. The explosion is not chaos. It follows physics with perfect discipline. Pressure moves into lower pressure, hot moves into cold, dense moves into sparse. But from our distant view, it looks like a flower blooming in fast motion. Layers of glowing gas expand into a shell, with tendrils and curves and colors, all born from the same quiet star that once sat peacefully among its neighbors. What was once invisible and controlled is now expressive and free. The supernova becomes an artist, painting the surrounding space with its own remains. And in this wave, there are gifts. The pressure and heat of the explosion cause elements to form that never could have existed inside the star itself. Gold, uranium, platinum. These heavy things are born in the blast, sculpted by the intensity of the moment. They are rare and beautiful, and they will float for millions of years before finding their way into something else. Perhaps into a planet, perhaps into a person, perhaps into nothing at all. If you were to freeze time during a supernova, you would see the star in all its layers unraveling at once. Like a bell that has been struck, it rings in every direction. Not with sound, but with light and particles and shock. The shape of the explosion is shaped by the star's rotation, its mass, its surroundings. No two are exactly alike. Some are round. Some are lopsided, some form jets, others expand more gently, but all of them sing in the same silent language of force. When it is over, there is no going back. The star that once was will never be again. In its place there is a ripple moving outward and a silence left behind. The symphony has played its loudest note, and the universe listens without needing ears. For a brief moment, a supernova becomes one of the brightest objects in the entire universe. Not just in its neighborhood, not just in its galaxy, but in the entire sky. It glows with a light so intense that it can overpower the combined light of hundreds of billions of stars. This is not a slow glow or a flicker. It is a burst, a flare of such radiance that even from thousands of light years away, it can be seen with the naked eye. Imagine looking up at a familiar night sky and noticing a new star where there was none before. It doesn't twinkle, it beams, and for a few weeks it seems to declare its presence without words. To those who witnessed such a thing centuries ago, it must have felt magical or perhaps unsettling. A new light in the sky, with no warning, no motion, no explanation. Today, we understand that what they saw was the death of a distant star, a grand exit written in light. But even with our telescopes and knowledge, the spectacle remains humbling, because when that light reaches us, it is old. It began its journey perhaps thousands or even millions of years ago, and only now has it arrived. A delayed announcement from a star that no longer exists in the form it once had. During its brightest phase, a supernova can cast shadows on distant planets. It can be seen during the day, rivaling the moon. But then, like all things that burn too brightly, it begins to fade. The peak of its light lasts only a few days or weeks. Then, it slowly dims, slipping back into the quiet dark from which it came. This gentle fading is part of the beauty. It reminds us that even the most powerful moments have limits. Even stars cannot hold on to their final shine forever. But what a shine it is! If you could stand on a planet nearby, one safe enough to survive the explosion, the view would be beyond anything you've ever imagined. The sky would be washed in light, colors would bleed at the edges. Even shadows would feel unfamiliar. The radiation would shimmer like a second Sunday. It would not be peaceful, but it would be beautiful. Astronomers track these explosions carefully. They measure the light curve, which is the way the brightness rises and falls over time. From that curve, they can learn things about the star that died, its size, its type, even its distance. In a way, the light of a supernova is not just a show, it is a message, a letter written in brightness, unfolding in the sky, and we are here to read it. When the light has finally faded, the memory remains. A supernova might vanish from sight, but its signature lingers in the minds of those who saw it, in the data of the telescopes, in the dust it left behind. The star may be gone, but for a little while, it outshone everything. A final blaze, a cosmic candle, and then quiet again. In the northern sky, nestled in the constellation of Cassiopeia, lies something that does not twinkle like the stars around it. It does not shine with a steady light, and to the naked eye, it appears as nothing at all. But through the lenses of modern telescopes, there it is, a ghost, a ripple, a slowly expanding cloud of gas and dust that marks the place where a star once was. This is Cassiopeia A, one of the closest supernova remnants we have ever found. It is not a supernova now. The explosion happened over 3 centuries ago, long before most of today's cities even existed. And yet, the echo still lingers. What remains of that ancient stellar death is a shell, a vast bubble of glowing material that continues to stretch outward at thousands of kilometers per second. The core of the star is gone. What we see now is the aftermath. Not a flash, but the cooling embers of an enormous fire. In the X-ray and radio wavelengths, the ghost comes to life. Filaments twist through space. Gases shimmer with faint colors. Each wisp and curl is a remnant of something that once burned with unimaginable heat. It is a picture painted not with brushes, but with pressure and light. Cassiopeia A is not silent. Though space does not carry sound, it does carry movement. The particles within the remnant still dance. They still collide. They carry energy, and that energy becomes something we can measure. It hums across the electromagnetic spectrum. It speaks in data. And what it tells us is that even hundreds of years after a supernova, the universe remembers. It holds the shape of the explosion. It holds the momentum. It does not erase so easily. One of the most remarkable things about Cassiopeia A is the tiny object at its center, a neutron star. Barely more than 20 kilometers across, yet more massive than the Sunday. It is a leftover from the star's collapsed core. It does not shine in visible light. It does not call attention to itself. But it is there, a spinning, cooling sphere of neutrons, born from a star that could no longer hold itself together. It is one of the most extreme objects in the cosmos, and it sits quietly in the shadow of its own origin. For astronomers, Cassiopeia A is a treasure. It is close enough to study in detail, and young enough that the echoes are still fresh. By watching it, we learn not only about how stars die, but about how they shape the space around them for centuries afterward. We see how gas moves, how shock waves travel, how the elements formed in that final blast begin their long journey toward becoming something new. To look at Cassiopeia A is to look at a memory suspended in time. A memory written not in words but in light and matter. It is not just the ghost of a star. It is the story of a farewell that was too bright to forget. In the year 1054, people around the world looked up and noticed something strange. A new star had appeared in the sky, bright enough to be seen during the day, even beneath the sunlit sky. It lingered there for weeks, slowly fading, but never quite behaving like the stars everyone knew. It seemed to arrive without warning and left without explanation. Today, we know what they saw. It was a supernova, one of the few in our galaxy bright enough to be recorded by human eyes before telescopes were ever invented. This particular event was recorded most clearly by Chinese astronomers. They kept careful sky records, tracking new stars and changes in the heavens. They noted this guest star near the horns of the constellation Taurus. It was said to shine for 23 days during daylight and was visible at night for nearly 2 years before it finally disappeared from view. To those watching, it must have seemed like a divine sign, or perhaps a mystery too vast to understand. Some Native American rock carvings suggest they too noticed it, etching spiral patterns and starburst shapes that may have been inspired by what they saw. Centuries later, astronomers would look back at those accounts and match them to something still glowing faintly in the sky. In the same place where the bright star once shone, they found the Crab Nebula. It is a soft, tangled web of glowing gas, still expanding from the force of the explosion that happened nearly 1,000 years ago. Within it lies a pulsar, a rapidly tropic, spinning neutron star that flashes like a cosmic lighthouse. That tiny, dense object is the collapsed heart of the star that people witnessed in 1054. It spins 30 times per second and sends out a rhythm of energy that travels across space like a faint drumbeat. When we look at the Crab Nebula today, we are seeing both the past and the present. The light from the supernova reached Earth in 1054, but the event itself took place about 6,500 years earlier, deep in the spiral arms of our galaxy. The light just took that long to travel across space to reach us. So in a way, we are catching up to the past, reading a story that was written long before the first cities were built. The idea that ancient eyes witnessed the death of a star is both comforting and astonishing. No telescopes, no equations. Just people standing under the sky, noticing something different and wondering what it meant. It reminds us that the sky has always been a storyteller, and humans have always been its listeners. The supernova of 1054 was not just an astronomical event, it was a moment shared between the universe and its observers, a soft flare in the heavens that whispered across centuries. And even now, the story continues to unfold in the tendrils of the Crab Nebula, spinning, glowing, echoing the light of a star that once said goodbye. You might not feel like a piece of the cosmos when you're brushing your teeth or walking through your day, but the truth is, you carry the story of stars in your very bones, quite literally in fact. Every atom of calcium that makes up your teeth, your skeleton, your heartbeat, and the quiet strength of your frame was born in the death of a massive star. Long before there were planets or oceans or people, a supernova cracked open the sky and scattered these elements into the galactic winds. That explosion, violent as it was, gave rise to the calcium that would one day become part of you. It is strange to think of our bodies this way. We are so used to the idea of being made from earth, from food, from the water we drink and the air we breathe. And that's true in one sense. But where did those things come from? The oxygen you inhale, the carbon in your cells, the iron in your blood, the potassium that keeps your nerves talking to each other, they all came from stars. And not just any stars, but ones that died in fire, ones that ended in supernovae. In the moments after a supernova explodes, the energy released is enough to force atoms together into new and heavier forms. Calcium, iron, nickel, gold, uranium, these are not ordinary creations. They need heat and pressure that go beyond what most stars can provide during their lives. It is only in their deaths that the necessary conditions exist. The shock waves from the blast force, these new elements outward, pushing them into the surrounding space. They float for eons, joining with clouds of gas and dust, becoming part of the next generation of stars, and eventually the planets that circle them. So when Earth formed, it inherited a treasure chest of ancient elements, and when life began to emerge, those elements found new homes in living things. Plants absorbed them from the soil. Animals ate the plants. People ate the animals and the plants. And through this quiet exchange, you became part star, not in a poetic sense, but in a very real, atomic way. It is humbling to realize that your body is not just yours. It is a collection of gifts from faraway stars, handed down through time by the universe itself. Every step you take is grounded in the memory of a supernova. Every heartbeat is powered by something forged in stellar fire. You are a walking archive of cosmic history, carrying echoes of explosions that happened long before there was anyone to name them. So, the next time you look up at the night sky, remember that you are not just looking at the stars. You are looking at your family tree, not made of branches but of light, not of names but of elements, and every bit of you that is solid, strong, and vital once floated through the silence of space, waiting to become something meaningful, waiting to become you. Not all supernovas come from the same kind of star, and not all of them go out in the same way. Like people, stars have different lives and different endings. Some live big and bright and fast, burning through their fuel with reckless intensity before collapsing under their own weight. Others live quieter lives, smaller, cooler, and longer, until one day they meet a strange fate involving a companion star and a very slow build-up toward catastrophe. Astronomers have sorted these stellar farewells into families. The two main ones are called Type 1 and Type 2. The names are simple, but the stories they hold are full of twists. Type 2 supernovas are what most people imagine when they think of a star exploding. These come from massive stars, many times the size of our Sunday. They live short, brilliant lives and die when their cores can no longer resist the pull of gravity. When the fusion stops, the center collapses and the outer layers are blasted away in a brilliant expanding cloud. These supernovas often leave behind something. A neutron star, a pulsar, sometimes even a black hole. They mark the end of a single star's journey written in glowing gas and scattered stardust. Type I supernovas, on the other hand, follow a more complicated path. They don't come from big stars. They come from small, quiet white dwarfs. These are the burnt-out remains of stars like our Sun, left to cool slowly over billions of years. But sometimes, a white dwarf has a partner. Another star nearby, often still burning with heat and light. Over time, the white dwarf starts to pull matter from its companion. It doesn't make a fuss. It simply gathers a little more mass, a little more fuel, like someone adding drops to a very full glass. Eventually, the glass overflows. The pressure inside the pression, white dwarf builds until it can no longer hold back. The result is an explosion just as powerful as any from a massive star. What makes these types even more interesting is how we use them. Type Ia supernovas, which are a kind of Type 1, all reach nearly the same brightness when they explode. This makes them incredibly useful for measuring distance in the universe. They are like cosmic yardsticks. If you know how bright the explosion really is, and you compare it to how bright it looks from Earth, you can figure out how far away it happened. This is how we learned that the universe is not just expanding but accelerating, all because a quiet white dwarf took in too much from a neighbor. So while the names Type I and Type II might sound like labels in a textbook, they tell stories of very different lives. One begins in solitude, ends in silence, and explodes from within. The other lives with company, steals a little too much, and ends in a blaze of unintended consequence. Each one is a chapter in the grand, glowing book of the cosmos. Each one is a different way for a star to say goodbye. White dwarfs are strange little things. They are what is left behind after a star like our Sun runs out of fuel. No longer burning, no longer expanding, just sitting quietly in space like a hot ember. Small, dense, and for the most part, forgotten. But sometimes, a white dwarf ends up in a very unusual relationship. It finds itself orbiting close to another star, one that still has fuel to burn. And in this arrangement, something sneaky begins to happen. The white dwarf starts to pull matter from its neighbor, not with violence or drama, but with gravity. A gentle siphoning that continues for thousands of years. Imagine a star sipping from the edge of another's light. The hydrogen and helium from the companion star slowly spiral down onto the surface of the white dwarf. It's a quiet process, a transfer of mass so gradual that it might be hard to notice even with a telescope. But all the while, pressure is building. The more mass the white dwarf gathers, the more tightly packed its interior becomes. The atoms inside it are already under enormous pressure, squeezed into a space the size of a planet. With each new drop of mass, the situation becomes more fragile. There is a limit to how much a white dwarf can take. It is called the Chandrasekhar limit, and once the white dwarf reaches this threshold, something happens that cannot be undone. The pressure inside becomes too great. The temperature rises past a tipping point, and suddenly, fusion reignites, not just in one place, but everywhere, all at once. The white dwarf, which had been silently gathering material for eons, explodes in a single stunning moment. Not a surface blast, but a full-body eruption. Nothing is left behind. The entire star is consumed in fire and scattered across space. This kind of supernova, called a Type Ia, is remarkable for a few reasons. First, it happens without a massive star. There is no giant collapsing core, no giant star burning through its elements, just a small, dense object that got too full. Second, the explosion is incredibly consistent. Because all white dwarfs explode at nearly the same mass, they produce almost the same amount of light. This makes them perfect for measuring distances across the universe. Like identical light bulbs scattered through space, they give astronomers a reliable way to understand how far away distant galaxies truly are. There is something quietly dramatic about this story. A star that lived a full life, shrank down into a tiny remnant, then waited in silence. It took nothing for so long, and then one day, just a little too much. It is a reminder that endings can come not from a single act, but from slow accumulation, from patience, from gravity, from the steady hand of time. The white dwarf does not intend to explode, but in the stillness of its orbit, it crosses a line, and the result is one of the most powerful explosions in the universe, all from a star that only wanted one more bite. A giant star lives its life on a scale that is difficult to imagine. It is vast, many times larger than our own sun, with layers upon layers of burning gas stacked like an enormous glowing onion. It spends millions of years fusing hydrogen into helium in its core, radiating light and heat into space. As it ages, it begins to fuse heavier elements, each new layer burning hotter and faster than the one before. Helium turns to carbon, carbon to oxygen, then to neon, magnesium, silicon, and finally iron. Each step comes more quickly, until what once took millions of years now happens in days. It is as if the star is racing towards something it cannot avoid. Iron is the last stop. It cannot be fused into anything heavier without costing more energy than it gives. And without the outward pressure from fusion, gravity begins to pull with nothing left to stop it. The core, once a furnace, becomes a weight. It grows heavier and denser, until the star's own mass turns against it. Slowly at first, then all at once, the core collapses. It falls inward with terrible speed, and the outer layers follow. In less than a second, the core becomes a ball of neutrons, and the rest of the star crashes into it. The result is not a slow fade, it is a sudden, violent reversal. The infalling material slams into the dense core and rebounds outward. A shockwave is born, racing through the star's layers, heating them, breaking them apart, and hurling them into space. The light from this explosion is so intense that it can shine brighter than everything else in the galaxy. For a moment, the star becomes something more than it ever was. Not just a source of light, but a beacon of transformation. This is how the heaviest elements in the universe are born. In the last seconds of the star's life, the shockwave creates conditions fierce enough to forge gold, uranium, and other rare materials. These are then thrown across the cosmos, scattered into space like a final gift. The star that lived to build becomes the star that gives away everything it made, and then quiet returns. What remains at the center is something entirely new. If the core is small enough, it becomes a neutron star. If it is larger, it may continue collapsing into a black hole. Either way, the giant that once lit up its part of the galaxy is gone. In its place is a glowing cloud of debris and a core that will never shine again. The death of a giant star is not a gentle thing. It is dramatic, sudden, and final. But from that end comes new beginnings. The dust and gas thrown outward will one day gather again, pulled together by gravity into new stars and planets. And so, the story continues. A tragic ending that seeds the next chapter. A star that gave everything so that something else could begin. After a massive star ends its life in a brilliant supernova, it leaves something behind. Not the kind of something you might expect. Not a glowing ember or a crumbling core, but something stranger. At the center of the explosion, where the pressure was highest and the collapse most intense, what remains is a neutron star. It is small, dense, and quiet. And yet, it is one of the most extreme objects in the entire universe. A neutron star is what happens when atoms are squeezed so tightly that their electrons and protons merge together. All that is left are neutrons, packed together like the densest crowd imaginable, standing shoulder to shoulder with no space between. The result is a sphere about 20 kilometers across, not much bigger than a city, but with more mass than the entire Sunday. If you could scoop just a teaspoon of it into your hand, which of course you cannot, it would weigh about 1 billion tons. That is how dense this remnant truly is. From the outside, a neutron star doesn't look like much. It has no fire, no light of its own. It may spin rapidly, especially just after the WOW, supernova, and this spin can cause it to emit bursts of radiation. But in the most basic sense, it is a dead star, not completely gone, but transformed into something unrecognizable. A fossil, not of stone but of pressure and light. These stars are not just dense, they are also stable. Once formed, they can persist for billions of years, slowly cooling as they drift through space. Some of them spin so fast that they seem almost unnatural. A few rotate hundreds of times per second. You would not be able to see this spin with your eyes, but instruments can detect the pulses of radiation they send out, and that steady rhythm reveals their astonishing speed. There is a strange beauty in how silent they are. No roaring fusion, no flickering brightness, just the slow rotation of something that has survived one of the most violent events in the universe. It is as if the star's last act was to become a whisper made of matter itself, compacted and frozen in time. Occasionally, neutron stars do strange things. They can suddenly change their rotation or emit bursts of high-energy light. These moments remind us that even in death, a star can surprise us. It is not truly gone. It still holds secrets. Most neutron stars drift quietly through space, alone. Others are caught in binary systems, locked in gravitational dances with other stars. Some of these pairs may one day spiral together and merge, releasing yet another burst of energy into the cosmos. But even on their own, neutron stars remain dense, silent, and steady. The final word of a once massive star, spoken in the language of matter itself, a star that lived loudly and now rests in perfect stillness, holding the shape of its collapse. Some neutron stars are content to drift quietly through the cosmos, holding on to the silence of the supernova that formed them, but others refuse to disappear without a trace. They spin rapidly, flickering like cosmic lighthouses, sending out beams of radio waves. As they turn, these are pulsars, and they are among the most precise and fascinating objects in the universe. From a distance, they appear to blink, not because their light flickers, but because their beams sweep across space like the rotating beam of a lighthouse tower. If Earth lies in the path of the beam, we see a pulse of light with every rotation. A typical pulsar spins many times every second. Some spin even faster, hundreds of times per second, moving so quickly that the surface of the neutron star is traveling at a significant fraction of the speed of light. Yet despite this incredible speed, their pulses are remarkably regular. You could set your clock to the beat of a pulsar. In fact, some scientists have joked that pulsars are the universe's most reliable timekeepers. Their rhythm is so steady that when they change, even slightly, astronomers take notice. It might mean the star has shifted, or it might hint at something unexpected nearby. The first pulsar ever discovered was met with confusion. It gave off such a regular signal that the scientists who detected it briefly wondered if it might be a signal from intelligent life. The pulses came so evenly, like a ticking metronome in space, that they were labeled with a playful nickname, Little Green Men. But soon, more were discovered, and the mystery gave way to understanding. These were not messages from aliens, they were the dying voices of stars. The light from a pulsar is not always visible. Most often, it is found in radio waves, or sometimes in X-rays or gamma rays. It depends on the age of the pulsar, its speed, and the environment around it. Young pulsars tend to spin faster and shine more brightly. Over time, they slow down and their beams fade. But even in old age, they remain detectable for millions of years. Their pulses continue, slowing like a music box unwinding, but never stopping completely. What makes a pulsar even more interesting is how much it reveals. By studying the way the pulses change over time, astronomers can learn about the neutron star's magnetic field, its structure, even its motion through space. Some pulsars are in binary systems, orbiting other stars or even other neutron stars. When these pairs move together, their signals shift in ways that allow us to measure gravity with incredible precision. It is as though the star, in its quiet rotation, is still telling a story. Pulsars are reminders that endings can echo, that the death of a star does not mean silence. Sometimes, what comes after is even more remarkable. A pulse, a rhythm, a spinning beam of light cutting across space, steady and bright in the endless dark. A heartbeat, still strong, long after the fire is gone. There are stars that die and leave behind a glowing remnant. Others spin and flicker like cosmic beacons. And then there are those that vanish entirely, collapsing so completely that not even light can escape. These are black holes, born from the deaths of the most massive stars. They are not objects in the usual sense. They are regions of space where the rules change, where gravity becomes so strong that everything falls inward and nothing comes out again. Not light, not matter, not even time as we understand it. When a giant star dies, its core may collapse into something too dense to stop. If there is enough mass, the neutron star that would normally remain cannot hold itself together. The pressure goes beyond what even tightly packed neutrons can resist. The collapse continues, faster and deeper, until the matter itself slips past a point of no return. That point is called the event horizon. Once something crosses it, it cannot come back. To the outside universe it disappears, but it does not explode. It simply folds inward, creating a gravity well so steep that even photons, the fastest things in the universe, cannot climb out. To imagine a black hole is to imagine something that cannot be seen. It does not glow, it does not reflect, it has no surface. Instead, it bends space around it like a weight on a soft sheet. If light comes near, it curves. If matter drifts too close, it falls in. And yet, despite this darkness, black holes reveal themselves, not directly, but through their effects. A star orbiting something invisible, a cloud of gas heating up as it spirals inward. Ripples in the fabric of space-time itself, created when two black holes merge in silence. These are the signs, the shadows cast by something we cannot touch. There is a quiet kind of awe in thinking about them, not because they are dangerous, although they are, but because they represent a place where understanding falters. The laws of physics, so useful and predictable elsewhere, become strange near a black hole. Time slows, distance warps. Inside the event horizon, we cannot say what happens. The math stops working. Some believe a singularity lies at the center, a point of infinite density. Others think something else may be hidden there, waiting for new theories to uncover it. But for now, we observe from afar. We watch stars dance around invisible centers. We detect the gentle tug of gravity on light. We listen for the hum of colliding black holes, which create waves that ripple through space itself. And in those observations, we find not fear, but wonder. These are not monsters. They are the silent remnants of enormous stars, gone not with a flash but with a folding, an end so complete that it rewrites the space around it. So, when a star dies and leaves nothing behind, do not think of it as lost. Think of it as hidden, a quiet presence in the night, drawing in matter and light, reshaping the cosmos one pull at a time. After the bright flash of a supernova fades, what lingers behind is not silence, not really. It is something more like a soft rustle across the stars, a breath held in the fabric of space. The explosion may last only weeks from our point of view, but the aftermath unfolds slowly, like the petals of a khas, flower drifting apart on a gentle breeze. These are the supernova remnants, the scattered remains of a star that once stood whole. They stretch outward through the galaxy, painting the darkness with threads of glowing gas and heavy elements. To look at one is to see a memory in motion. Each remnant is shaped by the star that left it. Some are nearly perfect spheres, delicate and symmetrical like soap bubbles. Others twist and warp with uneven bursts, shaped by the surrounding space and the star's final moments. The outer layers, once bound tightly together, have been flung outward in every direction. As they move, they carry with them the fingerprints of the star's life. Elements like oxygen, carbon, sulfur, and iron drift through the interstellar medium. These are not just leftovers, they are gifts. They are the building blocks of what comes next. In the center, there is often something strange and small, a neutron star or perhaps a black hole, but surrounding that core is a halo of color and light. Telescopes that capture different wavelengths reveal new details with each observation. X-rays show high-energy particles streaming through space. Infrared reveals dust warmed by the explosion. Radio waves whisper of charged particles moving in magnetic fields. Each frequency adds a new layer to the story, a story that began with collapse but continues in motion. One of the most famous supernova remnants is the Crab Nebula. It is still expanding more than 900 years after it first lit up the sky. The gas within it glows with eerie beauty, lit from within by the energy of a spinning pulsar at its heart. Other remnants, like Cassiopeia A or the Veil Nebula, show different stages of the same process. They are petals on the wind, caught in the long journey from death to dust. It is a process that never truly ends, only changes shape. The material from these remnants will not remain scattered forever. Over time, it will mix with surrounding gas, blend into molecular clouds, and fall into gravity's slow pull. Eventually, new stars will form, shaped in part by the old. And perhaps those new stars will one day give rise to planets, and those planets to life, and that life to thoughts, and those thoughts to wonder. All from a single star that burned too brightly and could not hold itself together. To watch a supernova remnant drift through space is to see time itself stretching out like smoke. It is peaceful, but not still. It is the gentle aftermath of something once furious, now quiet. A bloom in reverse, a memory with color, a promise that even endings can give rise to beginnings. It is easy to forget how much sparkle in the universe comes from destruction. The shine of a ring, the gleam of a necklace, even the trace minerals in your own body all tell a story of something long ago that ended in fire. When a star goes supernova, it does more than just light up the sky. It also reaches deep into the periodic table and starts making things that did not exist before. Gold, silver, platinum. These are not quietly forged during a star's normal lifetime. They are made in the furnace of collapse, in the pressure and chaos of the explosion itself. Before the supernova, a massive star spends its life building lighter elements. Hydrogen becomes helium, which becomes carbon, then oxygen, then heavier and heavier things, all the way up to iron. But iron is the end of the road. Once a star begins to build iron in its core, the process no longer gives off energy. It takes more to fuse than it returns. And so, the star cannot go on. It collapses, and in that collapse, everything changes. The pressure and heat become so intense that particles are slammed together in new ways. New elements form, elements heavier than iron, elements the star could never have created on its own. These heavy elements are rare in the universe, but they are not random. They follow the rhythm of a supernova's explosion. They form in the blast, wave, in the moment when everything is being thrown outward. Neutrons are flying in all directions, and under the right conditions they are captured by atoms faster than they can decay. This rapid process builds up the nuclei of gold, silver, and other precious elements, layer by layer, second by second. And then, just like that, the explosion cools, the process stops. But the elements remain. They drift out into space with the rest of the supernova's ashes. They spread through the galaxy, slipping into clouds of dust and gas, waiting to be gathered up again. Some of them end up in planets, some in rocks, some in oceans, some eventually become part of living things. That piece of jewelry you wear, that trace of gold in your blood, that sparkle in your electronics, they are all echoes of ancient stars. Stars that lived long ago, died in light, and left behind tiny fragments of themselves. Their sparkle is not artificial, it is a cosmic artifact, a bright remnant of a violent farewell. So the next time you see something shiny, remember that it may have started in a place far older and more powerful than anything on Earth. It came from a star's final moment. From heat and collapse, and the scattering of everything it once held, it is a reminder that beauty often rises from chaos, that the universe does not waste anything, not even a sparkle. In 1987, something remarkable happened. A star in a nearby galaxy exploded, and for the first time in modern history, we were ready to watch. Telescopes turned toward the southern sky. Cameras recorded the light. Scientists gathered data in real time. It was as if the universe had pulled back the curtain and allowed us to witness one of its most dramatic performances from a front row seat. This star, located in the Large Magellanic Cloud, became known as Supernova 1987 amperes, and its light reached us after traveling through space for about 168,000 years. Unlike other supernovas that were spotted centuries ago and studied only after the fact, this one arrived in an era when we could observe it with instruments across the entire electromagnetic spectrum. We saw it in visible light, but also in ultraviolet, X-ray, and radio. Neutrino detectors, which are rarely stirred by anything, picked up a gentle rush of particles just before the visible explosion. Those neutrinos were a kind of quiet whisper from the collapsing core, telling us the star had died before the light even bloomed. It was the first time we were able to watch a supernova unfold from nearly the very beginning. At the heart of this explosion was a blue supergiant star. That in itself was surprising. Astronomers had expected red supergiants to be the usual suspects for this kind of event. The fact that a blue star could end in such a way meant that something in our models needed adjusting. The universe had handed us not just a light show, but a puzzle. In the days and weeks after the explosion, a bright ring of gas began to glow around the supernova. This ring had been expelled by the star thousands of years before, during a quieter phase of its life. The shockwave from the supernova lit it up like a neon halo. Even today, decades later, we can still see the light expanding, and the ring continues to brighten as the blast wave moves through it. Every year reveals new details. The cloud of debris grows. The structure evolves. And we are still learning. Scientists hope to spot the neutron star that should have formed at the center, but for years it remained hidden. The core collapse was confirmed by neutrinos, but the remnant itself was elusive. Only recently have there been hints of its presence, buried deep within the expanding cloud. Perhaps it is shrouded in dust, or perhaps its light is just too faint. But the clues are building, and the mystery continues to unfold in real time. Supernova 1987 amperes is more than just an event. It is a continuing story, a chance to see what happens when a star ends its life with a brilliant farewell, a cosmic memory we are still unpacking, and a reminder that sometimes, when you look up at the sky, the universe is not just whispering its secrets. Sometimes it lets you watch as they happen. Not every supernova makes itself known with a blaze of light and a ripple across the sky. Some stars die in silence. No glowing remnant, no visible flare, just a slow dimming and then nothing. These are the so-called failed supernovas, stars that collapse directly into black holes without the usual firework display. To the naked eye, it might seem as though nothing happened at all. A star that once shone simply vanishes. One night it's there, and then, quietly, it is not. Astronomers began to suspect that some massive stars were ending this way when they noticed something strange in old telescope images. In a few cases, a giant star, visible for years, suddenly disappeared from view with no trace of an explosion, no burst of light, no afterglow. It was as if the star had simply blinked out. These observations hinted at a new kind of death, one where the collapse was too fast or too quiet to produce a traditional supernova. Instead of flinging its outer layers into space, the star folded in on itself and kept falling until nothing could escape. In a typical supernova, the collapse of the core triggers a powerful rebound that tears the star apart. But for some stars, especially the most massive ones, that rebound may never come. The outer layers fall inward, but there is no shockwave strong enough to push them back out. Gravity continues its work without interruption, pulling everything down into a black hole. In this case, the event horizon forms so quickly that light has no chance to escape. The star dies, with no final cry. Even though failed supernovas are invisible in the traditional sense, they still leave a trace. Sometimes, a subtle flicker of neutrinos may pass through our detectors. Other times, the surrounding environment shows signs of a disturbance, a flicker in brightness, a brief pulse of infrared radiation as material around the collapsing star is heated. It is like trying to study the shape of a stone by watching the ripples it makes when dropped in a still pond. The stone itself is gone, but the water remembers. One of the mysteries that remains is just how many stars die this way. If a significant number of massive stars end their lives in silence, it would change how we understand the life cycle of galaxies. It would also help explain why we do not see as many bright supernovae as we expect based on how many massive stars are born. There may be whole generations of stars that vanished quietly, leaving only invisible graves behind. There is something both haunting and peaceful about this idea. Not every end needs to be dramatic. Some simply let go and disappear, a final act not of light but of stillness. A reminder that in the grand story of the universe, even silence can carry weight. Even the absence of a star is a message, whispered in the space it leaves behind. It is natural to wonder what would happen if a star close to Earth suddenly exploded. A supernova sounds like something distant and poetic, until the question turns personal. Could one happen nearby? Would we see it? Would we survive it? These are the kinds of questions that drift through curious minds at night, and luckily, the answers are mostly comforting. The universe is vast, and space, for all its emptiness, gives us more protection than we might expect. For a supernova to pose a danger to Earth, it would need to happen relatively close, within a few dozen light years. Most supernovae occur much farther away than that, scattered across the galaxy like far-off lanterns flickering in the dark. When they do, we sometimes see them with our telescopes or even with the naked eye, but they do not come close enough to cause harm. Their light reaches us, but their radiation and shock waves do not. That being said, there are a few stars nearby that astronomers keep a gentle eye on. One of the most famous is Betelgeuse, the red giant in the shoulder of Orion. It is large, unstable, and expected to explode someday. But someday might mean tomorrow, or it might mean 100,000 years from now. Stars operate on a timeline that makes human history seem like a blink. Even if Betelgeuse went supernova tonight, It is located about 600 light-years away. The explosion would be bright, possibly even visible during the day for a short time, but it would not harm us. Its radiation would fade over distance, and the Earth would remain untouched. In the event of a much closer supernova, within 20 or 30 light-years, things could be different. The intense radiation could affect Earth's atmosphere. It might strip away parts of the ozone layer, allowing more ultraviolet light to reach the surface. Over long periods, this could influence life, but the odds of such an event happening nearby and within our lifetimes are extremely low. Most of the stars close to Earth are not large enough to end in supernovae. They will age and fade gently, like our own Sunday. Our Sun, by the way, will never become a supernova. It is too small. When it runs out of fuel, it will expand into a red giant, shed its outer layers, and then slowly cool into a white dwarf. No explosion, no blast of light. Just a soft letting go, spread over millions of years. So while it is true that supernovae are powerful and awe-inspiring, they are also rare and distant. The night sky holds many secrets, but it does not threaten us. It watches quietly, offering stories rather than danger. The universe gives us time, space, and a gentle buffer between the dramatic and the personal. We are close enough to see the beauty, but far enough to sleep safely under the stars that will one day say goodbye in silence or in light. In the shoulder of the constellation, Orion sits a red star that seems to flicker with quiet drama. The name is Betelgeuse, and it is one of the brightest and most well-known stars in the night sky. To the eye, it has a warm reddish hue, a gentle shimmer that stands out from the colder blues and whites of nearby stars. But behind that soft glow is a story filled with uncertainty. Betelgeuse is massive. It is nearing the end of its life, and someday it will explode. No one knows exactly when. It could happen tonight. It could take another 100,000 years. In cosmic time, that is the blink of an eye. In human time, it is more than 1,000 generations. What we do know is that Betelgeuse is a red supergiant, a type of star that often ends in a spectacular supernova. It is large enough, unstable enough, and old enough to be watched with more curiosity than concern. Its surface ripples and changes. It dims and brightens in ways that suggest a restless nature. In 2019, it dimmed more dramatically than ever before, and people around the world began to wonder whether its final moment had arrived. But the star recovered. The dimming was caused by dust, not death. A cloud of matter expelled from its surface drifted in front of it and blocked some of the light. It was not the end, just a reminder that stars are dynamic, especially ones this large. Betelgeuse continues to change, and astronomers continue to observe it with patient interest. They measure its temperature, they track its brightness, they study its spectrum for clues. When it does go supernova, it will be visible from Earth. At a distance of around 600 light-years, it is close enough to be noticed but far enough to keep us safe. The explosion will light up the sky for weeks. It may be visible during the day. It may cast shadows at night. But it will not harm us. It will be a show, a reminder that we live in a galaxy that is still writing its story. Betelgeuse has already lived millions of years. It has fused hydrogen into helium, helium into carbon, and so on. Now it nears the end of that path, building heavier elements in its core until, like others before it can no longer sustain the pressure. When that happens, gravity will win. The core will collapse, the outer layers will rebound, and a supernova will light up the sky. Until then, we wait, we watch. We admire the red glow in Orion's shoulder and wonder what secrets lie within it. Not with fear, but with fascination. Betelgeuse is a reminder that the stars are alive in their own way. They are not just points of light, they are stories in progress. And one night, perhaps in our lifetime, perhaps not, that red star will tell the next part of its story with a brightness that no one will miss. Galaxies are not still places. They may look calm in pictures, with their arms gracefully sweeping across the dark, but within those spirals and clouds, there is motion and change. Stars are born, live, and die. Gas moves in long currents. Gravity gathers things into clumps. And among the most powerful forces stirring it all are the explosions of supernovas. These single-star events reach across light years. Their effects are not local. They ripple through their surroundings, shaping the galaxy in slow, unstoppable waves. When a massive star explodes, it sends shock waves through the gas and dust that surround it. These waves move outward, heating the interstellar medium, pushing clouds together, and sometimes compressing regions just enough to start something new. This compression can trigger the birth of new stars. In this way, the death of one star helps create many others. A single supernova might give rise to an entire cluster of new stars, all born in the aftermath of one dramatic ending. But the influence goes beyond just creating stars. Supernovas stir the pot. They inject energy into the galaxy, keeping the gas from settling too quietly. This helps prevent all the material from collapsing too quickly into new stars. It slows things down, it spreads things out, it keeps the galaxy balanced between motion and stillness. Without supernovas, the rhythm of star formation might become too fast or too uneven. Their explosions help set the pace. They also enrich the galaxy. The elements created in the heart of a dying star are flung outward in every direction. These elements are carried by the expanding shell of gas, mixing with the raw hydrogen and helium of the galaxy's vast clouds. Over time, this makes the galaxy more complex. New stars born from these enriched clouds will have more ingredients than their ancestors. Planets will form with more variety. Life, as we know it, requires these heavy elements, and they come most often from supernovae. Sometimes, many supernovas go off in the same region, one after another, like fireworks set in sequence. The combined energy carves out vast bubbles in the galaxy. These bubbles can stretch across hundreds of light years, filled with hot, thin gas. They are called superbubbles, and their edges can glow with new stars forming, all sparked by the same chain of endings. So while a supernova may begin as the final act of a single star, its effects extend far beyond that moment. It shakes the space around it. It spreads light and energy. It changes the chemistry of everything nearby. It creates the conditions for the next generation. A galaxy without supernovas would be a quieter place, less creative, less alive. In the great swirl of stars, these explosions are not disruptions. They are part of the process, part of the way a galaxy breathes and grows. In every spiral arm, in every glowing nebula, you can find traces of past supernovas still echoing through the dust, a reminder that from endings come beginnings, and that galaxies, like stories, are always being rewritten. The universe is a patient recycler. Nothing truly goes to waste. Stars are no exception. Even in death, they leave behind the pieces that will become something new. A supernova may feel like a dramatic farewell, but it is also a quiet promise. It scatters the elements it spent its life creating, and those pieces drift through space, joining clouds, slipping into currents of gas, and eventually becoming part of something else. This is not just poetic, it is physical. The very atoms that once formed a burning star become ingredients for future stars, planets, and everything in between. This process takes time, a long time. After a supernova, the remains of the star expand and cool. The heavy elements it created in its final moments mix with hydrogen and helium. These enriched clouds of gas slowly gather under the pull of gravity. They may spend millions of years drifting quietly before they come together with enough density to form new stars. It is like watching the ocean rise and fall in slow motion, each wave a step closer to new life. Some of these clouds become nurseries. Inside them, gravity begins to squeeze. Small pockets collapse, growing hotter and denser until fusion starts again. A new star is born. But this star is different from its ancestors. It contains more than just the original ingredients of the universe. It has metals, carbon, oxygen, and other elements created in past generations of stars. Each star carries the fingerprints of the ones that came before it, and the cycle continues. The new star may shine for billions of years. Around it, planets may form from the remaining dust. Those planets will be shaped by the same elements once forged in the heart of a star that no longer exists. The iron in the rocks, the carbon in the soil, the nitrogen in the atmosphere, all are borrowed materials from a cosmic past. Even life, if it appears, is part of this recycling. Living things use these same atoms, reshaped and repurposed into cells, bones, leaves, and breath. This recycling is not random. It is part of how the universe evolves. Each supernova makes the cosmos more complex. Each round of star formation adds new depth, and with each generation, the chances for life, for chemistry, for change become richer. This is how galaxies grow old, not by fading, but by layering their stories one atop another. When you look at the night sky, you are seeing a timeline of recycling at work. Some stars are brand new, others are nearing their end. Some of the light you see began its journey long before Earth formed, and within that light is a history of transformation. Stars born, stars died, and stars born again. In the end, even the brightest explosions are not a goodbye. They are a turning point, a chapter ending so that another can begin. The universe does not forget. It reuses, it reimagines, and somehow, in the quiet between stars, it always finds a way to begin again. From far away, a supernova looks like a single flash, a quick, brilliant event that comes and goes in the blink of a cosmic eye. But when you watch more closely, with patient instruments and time stretched out across decades, you begin to see something else. A supernova is not just a moment, it is a story told in slow motion. Its beginning may be sudden, but the rest of its tale unfolds gently, like ripples spreading across a still lake long after the stone has sunk beneath the surface. In the days and weeks after the explosion, the light surges. The star shines brighter than it ever did in life, even outshining all the other stars in its galaxy. Then, slowly, it begins to fade. But the fading is not an end, it is a transformation. The expanding cloud of gas glows in different colors, depending on the elements it carries. Oxygen shines in green, hydrogen gives off red. Each glowing thread is a clue to what the star once was, and what it left behind. As the years pass, astronomers watch this cloud continue to grow. The shockwave moves outward, heating up anything it encounters. It stirs up nearby gas, it shapes the space around it. Sometimes, it meets a cloud of dust left behind by the star before it died, and the collision sparks new light, as if the echo of the explosion is still speaking. In this way, the supernova keeps telling its story long after the initial brightness is gone. Some of the light takes a detour. When the explosion first bursts outward, it lights up surrounding dust. That light reflects and scatters, and in some rare cases, it travels through space in loops and bends. Years later, this scattered light arrives at Earth from a slightly different angle. Astronomers call this a light echo. It is like hearing thunder a second time after it bounces off distant hills. These echoes allow scientists to study the explosion all over again, as if time has folded back on itself to offer a second chance. And then there are the waves we cannot see. The gravitational waves that ripple through space-time itself when two massive objects, like neutron stars or black holes, collide in the aftermath of a supernova. These ripples move silently, stretching and squeezing space as they pass. They carry no light, no color, but they tell the same story. A story of motion, change, and memory written into the shape of the universe. So while the supernova may begin as a blink, its afterglow lingers. It becomes part of the background, woven into the galaxy's tapestry. It lights up clouds, it creates elements, it leaves a core that spins or swallows or drifts in quiet solitude. It changes things. Not instantly, but over years, centuries, even millennia. To us, it may seem like an explosion, but to the universe, it is a long breath, a single word spoken slowly, a bloom in the dark that never fully closes. You are made of memories, not the kind you collect over a lifetime, but the kind the universe holds in silence. The calcium in your bones, the iron in your blood, the oxygen in your breath, all once belonged to stars that lived long before Earth ever formed. Those stars burned, fused elements deep in their cores, and when their time came, they let go in one final act of giving. They did not fade quietly, they burst, scattering their stories across space, and those stories drifted for millions of years until gravity gathered them into a new beginning. Every part of you carries some trace of that ancient fire. You are not simply made of stardust. You are shaped by stardust. The patterns in your atoms, the strength in your cells, the rhythm of your heartbeat, all whisper the echoes of supernovas that once painted the sky in colors no eye ever saw. It is a connection that runs deeper than poetry. It is physics. It is chemistry. It is history, written into the very fabric of life. When we look at the stars, we are not just looking out. We are also looking back. Their light travels for ages before reaching us. Some of the stars you see tonight may no longer exist. Their light is still on its way, but the star that made it has already burned out. In that way, starlight is a kind of time machine. It carries news from the past, and some of that news lives in you. You are the product of stars that exploded, but also of stars that came after. Stars born from recycled gas. Stars that carried the heavy elements into new clouds and new solar systems. The Earth formed from these leftovers, pieced together by the patient hands of gravity. Water filled the cracks. Life found a way, and all of it, every root and ripple and breath, comes from the elements cast out by dying stars. It is easy to feel small under the night sky. The stars seem so far away, so quiet, so eternal, but you are not separate from them. You are not beneath them. You are their result, their legacy, their continuation. In the most literal way, you are the universe, aware of itself for a short while, watching its own history drift across the dark. There is comfort in that, in knowing that you are not just passing through this world. You are made from it, and it is made from something even older, from fire, from pressure, from stars that lived and died and gave everything they had so something new could rise, something like Earth, something like forests, something like people, something like you. So if you ever feel unimportant, remember this. Your atoms have traveled farther than you ever will. They have been part of suns. They have floated through space. And now they are here, listening, breathing, dreaming. You are not just in the universe. You are the memory of stars. So, as you settle deeper and your breath finds a slower rhythm, remember that even the most explosive events in the universe eventually fade into soft echoes. A supernova may be a moment of cosmic thunder, but its legacy is quiet, drifting atoms, distant lights, a whisper in your cells. You are stardust, made from the remnants of things that once burned brighter than anything else. Sleep well, and may your dreams be full of galaxies unfurling, stars being born, and the gentle hush that follows the loudest goodbye.